Okay, I see it's 2 minutes past 2 Eastern Standard Time, and we are here to talk about charging electric vehicles. And what you see on the screen here, cars, buses, various things. What you don't see is the scooters and those cute little one-wheeled unicycle skateboard-like things, and a bunch of that stuff out there too, especially if you live in a university town. But we're here to talk about some of the well, we're just going to try to cover this topic as extensively as possible in the next 2 hours. And we'll get into some gory code details. We'll talk about some general stuff and try to be as comprehensive as possible. My name's Roger. I'm the guy here on your screen you're looking at. And I guess once upon a time we had a way of communicating. It looks like all we have is a chat box as far as hand raising and stuff is concerned. On the other hand, I think you have the possibility of a participant turning on their microphone. So if you have a question, and the whole idea here with the live webinar is to be able to do bi-directional communication, just as we're going to talk about bi-directional automobile charging as well. So in order to enable that communication, I guess what I need for you to do is just type a question into the chat box. We once had another box. I don't even remember the name of that box that we had the last time, but I don't see it today. Or if I don't respond to you, then feel free to open your microphone and say, "Hey, Roger, I have a question." And the worst I can say is, "Shut up, we'll get to you later," but I probably won't do that. So let's get going. We've got quite a bit to talk about. As you can see, there are a few different kinds of electric vehicles out there, but there's a whole lot more not in that picture, and times are changing. Vehicles, I don't know about that one in the lower right-hand corner, but they seem to be becoming quite popular in my neighborhood now. I've seen quite a few of those little new Tesla pickup trucks. Not sure if others have seen them as well, but all these are electric vehicle. Well, not the first two, but the last four are. And that electric motorcycle, I'm just wondering how Harley Davidson feels about that one. That looks like that could really do some interesting things. Anyway, when you got an electric vehicle, you got to put electricity into it, and that involves connecting it one way or another. So we're going to talk about that. Let's look at what's happening with EVs. Here's a little chart of projection based on Inside Climate News, Edison Electric Institute. It says that by 2030, well, where are we now? We're at almost 2025, but by 2024, with about 5 million, a little over 5 million EVs on the road by the end of the year. But by 2030, another 5 years or so from now, we're going to be up to 3 times that. 18 million or so, 18 and a half, 19 million. That's quite a few. And with that many cars, we're going to have to do stuff to make sure they're able to get charged. Now, in a single family detached, that's easy. Most cars charge overnight, can plug into a 120 volt outlet and get all the electricity they need for the amount of driving they're going to do the next day. And most single family detached that have a garage or even a parking area near them have a 20 amp outlet available for outdoor use of whatever. So in those cases, that's already in place for charging the vehicle. And we'll talk about what they can do. Parking areas like a parking lot. I pulled into a parking garage when I went to a doctor's appointment a couple of weeks ago, and they had probably 30 or 40 chargers for EVs on 2 of the levels, which it's a new parking garage, and we're going to see a lot of them in places where people park. And if you got a motel that has an EV charger that will allow somebody to dump 200 to 300 miles of driving in their car overnight, you are certainly going to be preferred over the, if you have an electric vehicle, if you're one of those 18.5 million, you're going to be going to these lodges to charge your car, and they're going to sell out fast. And then there's condominiums like where I live that sooner or later maybe we'll wake up. But I've had some very interesting experiences talking to condos about providing charging for electric vehicles. The one right next door a year ago had if you plugged your electric car into a 120 volt outlet in the building, it was an immediate $250 fine. So there's a lot of weird stuff going out there, a lot of bad information, disinformation out there on vehicle charging. We're going to try to have a look at some of that today as well. So this is kind of what we're looking at, and this is why we're here today, to talk about how do we deal with all these electric vehicles if we are in the engineering business, other than just driving them. I will acknowledge that I've been driving or my family has been driving a plug-in hybrid electric vehicle since 2018. We're getting roughly 1,500 miles to the gallon because mostly we drive less than 30 miles a day, and we're able to charge it up at night on a 120 volt charger and have all we need for the next day. So filling up the gas tanks about twice a year is all we need to do. We've built that as an in-between. We're looking at new batteries and things, and that car will probably go to somebody else in another year or two. So let's talk about the types of EVs. And here's something in the chat. What do we got here? How do you keep the gas from going bad if you fill up just 2 times a year? Interesting question, Phil. There's actually something you can get from the, and I can relate to that because I used to have to my lawnmower every winter that I put the lawnmower to bed, and then the spring I'd have to dump the gas and it all messed up. But there's okay, Stabil, is that what it is? I don't remember. That sounds like it's stabilized. There's some stuff. I've just been putting premium gas in with the thing, and we've done okay for 6 years with that. But you can also at the dealer get this fluid you can add that prevents it from turning into jello. Excellent question, though. But yeah, I was a little concerned about that, but we've managed 6 years, so I'm fairly confident we'll go a little further. And thanks for that question, by the way. I appreciate it. It also tested out whether we're able to use the chat box. Okay, so what are the kinds of, let's get a little background here. EVs, if it's all electric, it has an electric motor and no gasoline backup, it probably get between 100 and 400 miles. Battery storage between 30 kilowatt hours and 100 kilowatt hours. My guess is everybody out there can probably read their screen, so I do not need to read every word to you. And furthermore, if you really want to get this stuff down pat, you might want to go over it again. And I encourage you, that our hosts will have available PDFs of this presentation that you are welcome to download for no charge and use to the extent you care to use them. Show your friends whatever you want. The whole idea is get the word out of what's really true about what's going on here. And I've made a lot of effort to make sure that what's here is factual, actual, and legitimate engineering stuff. Okay. A plug-in hybrid is a little bit different. It's a hybrid car that has a little bit bigger battery pack. Ours in particular stores 17 kilowatt hours. And you can plug it in overnight. And our electric range is about 50 miles, but we can get another 350 with our 8 gallons of gas in the tank. So if we really need to go somewhere, we can get, if we wanted to bail out in case a hurricane came by, we could almost drive out of Florida from where we are in South Florida right now without having to stop at a gas station or someplace to plug in to charge up some electric. Most of the cars have lithium-based batteries. That's important because they don't require any ventilation during charging. They don't give up any hydrogen like the lead acid batteries do. And charging times vary depending on charge level. We're going to talk a lot about charge levels, charge times, and stuff like that. So those are the two types of EVs out there right now, and this is vehicles that drive on the road. And if we look at code references, National Electrical Code 625 is where you go if you want to specifically look at charging electric vehicles. Section 2 tells you what are the typical electric vehicles out there that are intended for driving on the road. And electric golf carts aren't intended. And also they have to have rechargeable batteries. You can't just put in, throw away your batteries and put in fresh ones. You have to recharge them. And that means that you can't use these kind of batteries in your electric vehicle because these are the old-fashioned hearing aid batteries, and you had to throw those away when you were done. So let's just look at comparative costs, whether it's even worth it to drive an electric vehicle. Fuel costs for 1,000 miles for typical vehicles. And we have to, and these are numbers that will vary almost a daily, weekly basis. In fact, for me, in case when we buy gas twice a year, there's no way to predict what the gas price is going to be when it's time to buy it. But let's just assume $4 a gallon and 15 cents a kilowatt hour. Both of these can vary a whole lot, as you know, and you're welcome to put in your your own numbers if you have something different, and the process is the same. If you got a full-size SUV that gets 20 miles to the gallon, very straightforward. 50 gallons of gas for 1,000 miles, you got $200, or 1,000 miles at $200. That's what's that? That's 50. No. Yeah, $4 a gallon, $200 for 1,000 miles of driving if you get 20 miles per gallon. Okay. If you have a small SUV at 30 miles a gallon, then your gas bill drops to $133.20 for 1,000 miles. And of course, that's for what, 1/12 of a year or something. Typical vehicles driven about 10 to 12,000 miles a year. So this is about a month's worth. And for a hybrid sedan at 55 miles a gallon, you're looking at $72.80 for operating costs. If you've got a electric vehicle operating on electricity only, you're down to $37.50, and that's at 15 cents a kilowatt hour. If you can buy off-peak electricity for 5 cents a kilowatt hour to charge your car, then you're looking at $12.50 for 1,000 miles of driving. Ain't bad, not too bad, pretty cheap. And we're not even talking about maintenance costs and so forth. There's a whole lot of stuff you don't have to maintain in an electric vehicle that we have in well, like a radiator, for example. You can always tell when a gasoline vehicle has been out for a ride because you just touch the hood and it's warm. You get an electric vehicle, it's been out for a ride, parks it, you touch the hood's cool. There's something about heat and loss and transition and heat engines and second laws of thermodynamics. They're all that apply here. And electric motors, a little bit different story, a whole lot more efficient. So, and then of course, if you have a plug-in HEV that goes half and half, you're still at 58.75 for that 1,000 miles. So we're looking at pretty good economics in terms of fuel costs alone. And why would somebody buy one of these? And unless they find out it goes 0 to 60 in 2 seconds, which is another issue that some folks probably are thinking about. I remember my first ride in a Tesla, I thought I was going to lose my stomach. It just went right on up into my throat when the guy stepped on the gas. We don't do that with our little plug-in hybrid. We just drive it like a regular car. But there's other things that attract people to cars, and Tesla makes a lot of the sports cars look like they're, anyway, well, that's not what we're talking about today. Let's compare carbon dioxide, though. That's also interesting because we're dangerously close to that carbon dioxide level, which is believed by many to be an unstable situation, which could lead to thermal runaway and global climate change for those who believe in climate change and temperature increase and understand the greenhouse effect and things. So if this is of concern, here's what you do with 10,000 miles on a renewable electricity with electric vehicle. Cost you about $450, pretty clean as far as the emissions. And the electric batteries are available for utility storage when the vehicle's at charging station. Well, now this is yes and no true. It's interesting. I was just reading my recent article from the Union of Concerned Scientists, and California has now passed a law that says that electric vehicles now, they're encouraging them to be bidirectional so that you can park it. And if the utility wants to buy some electricity from your storage tank, which may be 80 to 100 kilowatt hours, your car is allowed to negotiate a rate for selling that electricity. So let's look at the gasoline vehicle. 10,000 miles, 25 miles a gallon, sort of an average for a fleet. 400 gallons of gas, $1,600 as opposed to 450. I can attest to these numbers in terms of cost. I've lived with that for 6 years now. 7,840 pounds of carbon dioxide released. So that's, by the way, that's 3.56 metric tons. And if you do that with a fleet of 275 million, like we have on the road here in the United States, that's going to give you 980 million metric tons of carbon dioxide released in a year. That's a lot. Now, one would argue, wait a minute, electricity, there's carbon dioxide produced when you make electricity. And yeah, it's about 0.92 pounds per kilowatt hour, which means the electricity and your equivalent carbon dioxide per mile with an electric car is roughly 75–80% less than what it would be with a gasoline car. So just as a comparison, to be fair, that yes, the electricity for the moment is mostly, well, it's a mix of things, but most utilities now are down to mostly natural gas, some coal, but they're working fast to move from coal to natural gas, and they're building a lot of big photovoltaic facilities and a lot of storage facilities. And there's nuclear out there, and there's some wind and stuff. So about 0.92 pounds per kilowatt hour is the average CO2 production in the United States per kilowatt hour. Some areas more, some less, depending on the mix of the generation. Let's talk about charging levels, get that down. Level 1 is the 120 volt charger. And they're typically on a 20 amp circuit, but most of the chargers that come with the car are designed so you could plug them in even to a 15 amp circuit. So maximum charge rate on a 20 amp circuit is 16 amps or 80% of that, which would be 1920 watts. If you have a 15 amp circuit, then you're going to have to have only 12 amps. So that gives you 75% of that as a charging rate on a 15 amp circuit. But even that, it gets you ready to go after 8 or 10 hours of charging overnight for the next day, for most uses, unless you are traveling salesperson or something. Level 2, you can run that on 208 or 240. They're all everyone I've seen has still been a single phase outlet because that's mostly what's available. And they charge at somewhere in the range of 3,800 to 19,200 watts. And that's all level 2. And so you can see the size circuit breakers you need for the various levels of charging. And we're going to talk about how do you determine whether or not an existing electrical service can manage to put in a particular charger or whether you're going to have to do a service upgrade. So that's one of the things we're going to talk about today is how do you incorporate these now into the existing electrical system, how many modifications might need to be made. Level 3 is in the 50,000 to 350,000 range, and even higher now for some things like buses. But this is, we're talking up to 200 amps and at 1,000 volts or 420 amps at 480 volts. So this is not something that's a residential option. But it is something you get out if you want a fast charge when you're driving from point A to point B where you're 300 miles apart and you want to stop after 150 miles for a hamburger and you want to put 150 miles into your electric tank or in a half hour. Level 3 charge is what you do that, and you pay a little more for that. Typical level 3 is closer to 50 cents a kilowatt hour, which gets it closer to the price of gasoline. But then again, level 3 is not particularly cheap in terms of, you can imagine what it would cost to put in a 420 amp, 480 volt service. That's not at all cheap. So you got to amortize that some way. So level 1 and level 2 chargers, they deliver AC to the vehicle. And then the vehicle converts it to DC. And of course, if you want to send it back to the grid, then you need another inverter in the vehicle. Just like in a residential photovoltaic system that has battery backup, which the batteries have to have an inverter they run into in order to produce AC to run the house. And that AC can run back to the utility. You can do the same thing in a car. Technology is already here. Very well understood and very reliable, and economics are good. Level 3 chargers, though, they are just DC. The losses involved in the DC to AC conversion are hardly worth it with a DC charger. So a couple of examples and pictures there. How long does it take to charge? I mentioned charging overnight, but let's just take a look here. Typically, the range of most EVs out there now is between 3 and 4 miles a kilowatt hour, and that depends on kind of how you drive. If you're using your air conditioning and radio and lots of other electrical stuff inside that has to run on your batteries, that's a bit of a drain as well. But if you're just using your batteries for driving a car and no other electrical applications, you could get up to 4 miles a kilowatt hour. I like to use 3.5 miles. That's fairly typical, and that seems to be about what we get with ours. So that's pretty good number to work with, and that's what we're going to work with as we go through here. So conclusion we can reach is with a level 1 charger, if we have 1,800 watts, that's about 6 miles per hour of charging. In other words, 1.8 kilowatt hours. And every hour that gives you, in other words, 1,800 watts for an hour is 1.8 kilowatt hours, and that's 6 miles. And if you're charging at slightly less, then you're looking at about 5 miles an hour. So 5 miles an hour is a reasonable thing for estimating how long you need to stay plugged in on a level 1 charger, because you may not be able to charge at an 1,800 watt rate. In any case, it doesn't make a difference whether you're plug-in or electric, because both use about the same motor. So you got about 6 miles an hour to the battery charge. And so 6 miles per hour, that's a very interesting electrical unit, isn't it? 6 miles per hour. But that's kind of one way to look at it. Level 2, let's say we got 8,320 watts. That means that, gee, that's a whole lot more than 1,800. That's 4 times as much, isn't it? So then that looks like we ought to be able to have or almost 5 times as much. So this gives almost 30 miles an hour for charging, right? And most cars, we drive ours about 15 to 20 miles a day. So on a level 2 charger, we can charge a day's worth of driving in less than an hour. which means that very same charger, if we're willing to move our car and let somebody else pull in, and by that charger could do 24 cars an hour or 24 cars a day. Or if that same available power could be spread around to 24 different chargers on that same circuit that only operate one at a time, then you don't have to move the car. You just share, and we're going to talk about that too, about how chargers talk to each other and communicate to limit the total power they draw out of a particular circuit. Level 3 at 120,000 watts, half hour gets you about 200 miles of driving, not bad. Of course, you can get more than 200 miles of driving with gasoline, on the other hand, in less than half hour. But these things are changing as we speak, and chargers are going up at the charging time, and there's going to be ways to do that. In any case, no matter how you're charging, level 1, 2, or 3, once you get up to about 80%, whether it's with your phone charging or anything else you're going to plug in to charge your computer, once it's charged up to your laptop, it's charged up to about 80%, it slows down a little bit. And you can even do that experiment. Plug it in and draw yourself a graph. Every 5 minutes, check what percentage you're at charge, and you'll see that it just kind of levels off and reaches 100%. There's a important reason for that, because lithium does not like to be charged over 100%, and it's got a very, very sophisticated charge limiting mechanism within the battery system itself to make sure it does not charge beyond 100%. Okay, so charging times. We drive 10,000 miles a year. Let's just do this a little backwards here. 27.4 miles a day. Why not 30? All right, level 1, 6 miles an hour, 5 hours a day. Level 2, 1 hour a day. Okay, so if you drive your car 10,000 miles a year and you decide you're going to go to a level 2 charger in your garage, that means you're going to use it one hour a day. Or if you have 2 cars, then you can have 2 outlets and they can share. And in 2 hours, you got 2 cars charged up. Okay, and if you've got some excess renewable energy available during the day, then an electric vehicle is a fine place to store it. So if you, for example, have PV on your house and you want to save it, then plug your car in during the day. And Tesla and a lot of the photovoltaic folks have now got provisions to have your charger talk to your photovoltaic system and use any extra electricity it's got when it's available. So 18 hours a day on a charger, you can charge 3.6 EVs a day on a level 1 circuit, 18 of them at level 2 or 40 amps. Okay, so you get the drift here that a lot of these stories you hear about all this electricity and all this huge things you need. The idea here is load management and sharing of these resources. So now we start looking at design rules. But these are some important observations, some numbers. So now we can look at how to design these things. What do we want on a decent charger? We like to be compatible, likes to communicate, time, cost, safety, code compliant. Here's a typical connector, and you can see the pins on it. The big ones on the right-hand side are your power, and that could be either 120 AC or 240 AC. The big one at the bottom is your ground, and the 2 little ones are your proximity detection, but that's basically your communications network. But it also will not allow your car to drive away when it's plugged in. You got to unplug it before you can drive away. Advanced charger, bi-directional. Hello, California. Adaptable, portable, smart. You know, dial up with your phone, load management on it, have it network, let it do billing. Big fuss and condominiums about who's going to pay for the electricity. Well, let your charger communicate with some centralized billing mechanism within your condo so they can bill you for the electricity you use in charging your electric vehicle. Most condos, the big ones, they're on a demand schedule. So that means if you've got a demand schedule, you're going to have a charge for energy and you're going to have a charge for power and demand. And the energy for the kilowatt hour charge in my building is 8 cents a kilowatt hour. So if I stay off peak demand, the electricity I'm putting in my car is 8 cents a kilowatt hour, not 15, but 8. All right, so anyway, here's desirable features in a charger. All right, and here's some typical level 1s and level 2s. There's a level 1. That thing on the left is a special transformer that determines if there are any ground faults. There's some communication stuff in there so that it'll talk to your telephone by way of Wi-Fi, things like that. A lot of things on pedestals, wall-mounted, ground-mounted. Here's one at a local library, and here's one at a local university. Where you drive up, and if you're lucky, and it looks like there's a few spaces available here, a couple of these, you can plug in, and some of them, you just plug them in and you get your electricity complements of the facility. So that's also a nice feature. I've noticed that a number of the waiting areas at airports where you're waiting for passengers to arrive in the parking lots, you can plug in. So, and some of these can actually convert between level 1 and level 2 with an adapter. Level 3s might look like this. The whole idea being it's about a half hour to go into that McDonald's, and in that half hour you get 200 miles with that fast charger. You can see that the connectors are a little different here. Those two big things, we're talking 100 amps here now, so you need a whole lot fatter wire to get 100 amps of charging. And then there's your communication wires and your ground, your DC on the bottom there. And here's the, if you want more detail on it, this is the description of all terminals on this particular J1772 DC charger. Okay, so useful to know some standards and codes. Let's just take a few look. National Electrical Code, here's bunch of sections in NEC. 625 is specifically automobile charging, but 220.82 is sizing your service. NEMA's got a lot of standards for different connectors. The SAE J1772, so that you don't have a different kind of connector for every different car. The Open Charge Point Protocol. That way the chargers can talk to each other. UL 2202 is a standard for EV charging, and if you want one of those, it's a mere $1,000. If you're going to build EV chargers, it's not a bad idea to have one of those handy. 2231, personnel protection, and 2231, personnel protection systems for EV supply circuits, and North American Charging Standard is one that's being worked on. And by the way, we're talking all about wired chargers. There are also wireless chargers out there that they are working on. There are still a few issues they're trying to deal with, one of which is radio frequency interference, and the other regular electromagnetic interference, but the also possibility of health issues if they're not properly managed. So they are charging some electric buses and things, and it's some experiments where you just drive over this coil in the road and it couples to your vehicle at a higher frequency, like 50 kilohertz, and charges your batteries fairly fast. And there seem to be some successful experiments going on there. This is all we're going to say about those in this particular presentation. If you want to read more, here's a nice reference about various codes and standards. And here's another one. Wikipedia's got a nice thing on open charge point protocol. A little more NEC 625. An electric vehicle storage battery does not release gas. Not allowed to do that. Has to be fastened in place. Well, it doesn't have to be, but if it is, then it can be removed without a tool. If it's fixed in place, then you need a tool to remove it, your charger, that is. Gives nominal AC voltages that are available. And again, I'm going to flip through these fairly quickly just so you know they're out there. And if you're seriously interested, just go to National Electrical Code and 625, and it references a lot of other parts. The important one is 625.41, because if you want to add an electric vehicle charger to an existing service, this tells you how to do it. And it's very simple. 100% of the non-continuous load. In other words, you calculate your load on that panel using your, 10,000 watts at whatever, and then add your EV in as though it were an air conditioner or a new similar load that runs continuously. And so an important thing that's easily missed here is that the feeders to the distribution panel have to be rated also as 625.41. So, for example, if you have 2-aught feeders to a 200 amp feeder panel, that's fine as far as the 200 amp panel, but the 2-aught feeders are not rated for 200 amps continuously. So for continuous 200 amps, you need 3-aught copper feeders. So that's an interesting thing. And then you get into whether your terminals are 75 degree or 90 degree and a little more detail. So we want to stay a little more general than getting into the gory detail. We'll just do details, but not gory details here today. But 625.41 is a good one to look at. And here's some other stuff about lockable disconnects and so forth. Okay, lots of different rules. And here's the interesting one, the 625.48, another interesting one. Interactive systems with references to NEC 702 and 705. National Electrical Code 705 is connecting a system to the utility and delivering power to the utility. So all the rules are already laid out in all the National Electrical Codes, at least since the 1970 or the 2020 edition. And UL 1741 applies to these systems as it does to photovoltaic systems and any other renewable energy system that wants to sell electricity to the grid. So this one is coming up fast. California is the leader, but other states are following along, and you can bet within a couple of years, well, depending on the state, how progressive they are. I think they're going to be following California's lead, because it's a great way to have a whole lot of extra storage available, especially if these cars are parked in a garage at work or home at 4 o'clock in the afternoon, fully charged from renewable electricity that was generated earlier in the day, and now available to deliver power to the grid during grid peak time, so they don't have to turn those peaking generators on, the fossil-fired peaking generator. So this one's going to be interesting. Watch out for it. Have to have a charger more than 18 inches above the floor. That's the standard rule for electrical outlets in a garage. Why is that? Because gasoline vapors generally hover close to the floor, and we wouldn't want to start any fires, would we? Okay, so a little more 625, and again, I'm going to flick right on through because we want to get to calculating the service size. Let's check our time here. 241. Okay, so looking at 220.83 for existing single family and 220.84 existing multifamily dwellings. What do we got? And this for residential. Other sites like motels, hotels, commercial, whatever, there may be other sections of the National Electrical Code as well. So we're going to do some residential stuff here. We're going to start with a 1,500 square foot dwelling. Not going to add any new loads, just a new charger, and let's see what we got. And the load calculation might look something like this. Electrical engineers probably familiar with it. Others, if you're working as PEs, and more than likely you are, otherwise you wouldn't be taking this course, you have probably seen electrical load calculations on plan sets. So we're looking at general lighting, 3 volt amps per square foot, 4,500. Washer, dryer, refrigerator, 4 appliance circuits, add them all up. I don't have room on the screen to put them all in a line, so we added them up 13,900 volt amps. An electric water heater, an electric range, another 16.5. That totals up. This is your diversifiable load, 34,900 volt amps. So now, since we're not adding a new load to this, we're looking at it, or we are adding a new load. So we're looking at we can take the first 8 kVA at 100%, so there's 8,000. The remainder at 40%, that's 10,760. We can take 65% of the 10 kW of electric heat, and that's 6,500, and then that's what we would have done even without the EV. And now we take our 7,680 volt amp EV charger, but what we need to do, if we follow that 625.41, we need to take 125% of that and consider it as a continuous load. Even if it only runs an hour a day, we need to consider it as continuous, because who knows, you might have 3 cars, 4 cars. So 125% of the 7,680 is 9,600. This gives a total load on the feeder of 34,860 divided by 240 volts, minimum service size 145 amps. Okay, pretty straightforward. And it means as long as the existing service is at least 150 amps, and a lot of them are, especially if the building has air conditioning, then the charger can be added. And if that's as long as there's room for a 2-pole 40 amp circuit breaker in the main distribution panel. If not, you may still be allowed to do a tap at the service. But in any case, if you didn't have that charger, your load would be 25,260. Whoa, volt amps, not kVAs. Typo, Roger, you goofed up. Anyway, it's 105 amps instead of 145 amps. So you're picking up the extra 40 amps, which is what we installed. We installed a 40 amp charger. Okay, so effectively then, the bottom line is if you want to put in a 40 amp charger, it adds 40 amps to your electrical service load. So whatever your load calculates out, you add 40 amps to it and see how that adds up. And if it still stays within your size of your service, then you're good to go. Now, of course, that's using the 220.83. And if it doesn't quite make it with 220.83, 220.84 allows you to calculate your maximum demand, what you really use, which might be less now with more efficient air conditioning, more efficient lighting, more efficient almost everything. But the problem is you have to either have billing information for a year, which is great if you've got a general service demand rate, because you know what your demands are every month of the year. But in residential, you're not going to have that. So then you have to actually instrument the thing with recording ammeters on both lines to see what happens for a whole month. You're probably not going to wait for that. So anyway, the 220.84 is great if you got a general service demand rate. But otherwise, this is just an example of most residences can probably accommodate a 40 amp charger. And that 40 amp charger, as we showed earlier, will pretty much charge your 30 miles a day of driving in 1 hour's time. But if you drive 90 miles a day, it's going to take you 3 hours. But in any case, it's rarely necessary to use any more than a 40 amp charger, and maybe less. And the nice thing about chargers is you find in your load calc that, oh my gosh, I can't get 40 amps, I can only do 32. Your charger can be programmed to limit with power control system type limiting to 32 amps. So you can also do some power limiting rather than service changing. And at 32 amps, well, then you're at 80% and of 30 miles. So then you're doing 24 miles an hour charging instead of 30 miles an hour charging. Okay. So the alternate service calculation is U20.87, but that's what we were just talking about. So you're not likely you're going to do that. Okay. On the other hand, 220.87 is great if you're in a building with general service demand, and we're going to do that next. All right, what if we have a three-phase service? Let's say a 122.08 service. What can we do with it? Let's say, for example, how many 16 amp 120 volt chargers can it supply? And by the way, I haven't looked up here to see if oh yeah, there's somebody on the chat. Let me see what's in the chat. I'm sorry about that. Unless I specifically touch that part of my screen is 100% full of the slides. Let's see what we have here. Do you think the SAA standard plug will fade away with Ford and GM's adoption of Tesla's plug? Good question, Dave. This one, I think Ford and GM they're pretty big outfits, and it's probably likely that it will ultimately fade away, but it may take a while because there's a lot of them out there. So maybe we'll see side by sides or something. I'm not exactly sure how that will be dealt with, but it's a good point that and standardization is good. And one interesting thing here is that and this is a question I want to ask too, by the way. At some point, we're going to take a quick break, and I'm going to open my participant box, and I'm asking everybody who has an electric vehicle or an interest in an electric vehicle to raise their hand. In fact, let's do that now while we're thinking about it before we go into this three-phase thing. How many people out there? Let's see if we can find the raise hand buttons and see if they even work. Dave's got one. Who else has an electric vehicle out there? Nick, Patty, George. Y'all driving Teslas? You got something different? Well, that's pretty good percentage. We have 4 out of 26. That means we only got 22 more to go. Who knows how many of the 26 after this will probably just run right out and buy an electric vehicle. I'm going to wait another year, frankly, because they're coming out with some really interesting batteries, some of which presumably have 800-mile range. Solid-state batteries the Japanese are looking at. But in any case, yeah, hopefully this will be useful to the EV folks. And in terms of the interesting thing is the important thing about the standardization of the plugs is places where everybody and their brother plugs in. There maybe will have an option, just like at a gas station. They're not totally standardized on regular gas. You get choice of 3 different gases or so that you put in your gas tank, and it could very well be they'll have 3 different connectors there that you can connect up with in order to fill. And that may happen for maybe a period of 10 years or so before we're down to a single connector. My guess is that's probably what we're going to see here for a while, at least for the time being. All right, so here we go. How many 16 amp 1920 watt chargers can we supply? Well, single phase, so therefore they connect line to neutral. continuous load, so therefore we have to size the circuits at 125%, which means the charger has to be on its own circuit with 101 pole 20 amp circuit breaker, because 125% of 16 amps is 20 amps. So the question then is, how many of these single pole 20 amp circuit breakers can we connect up to this 200 amp service? And well, there's no diversification factors in NEC for multiple chargers, like they do for ovens and things like that, or multiple units in a condominium. So we can't diversify it. NEC does have provisions for multiple chargers, though, by the way, because they let the chargers talk to each other and limit themselves. But the feeder is rated at 200 amps, then the maximum load on the bus bars has to be 160 amps or less. All right, that's that 80% rule. So that means we only have 160 amps left to deal with. So on a balanced three-phase power system, power is going to be 1.73 times 2 times the line-to-line voltage times line current, or 57.64 kilowatts available for charging from this panel. Excuse me. So let's see what we can do with that. 57,640 divided by 1920, that's equal to 30. That's interesting. We should be able to do 30 chargers. Let's see how we might hook those up. That would be 10 on each phase, wouldn't it? So what happens if we check out the line currents with that? So let's take a look at a three-phase panel and see what happens here. My computer screen isn't long enough to put in all 30 of them, but we can do 12 of them and get the idea. If we connect one on phase A, B, C, and then go A, B, C, A, B, C, A, B, C, A, B, C again 4 times, gives us 64 amps per phase for 12 chargers, a total of 23,040 volt amps total. And do a little math here. 12 chargers times 16 amps times 120 volts is 23,040 volt amps. Okay, that's and so 30 chargers, we would expect 30 times 16 times 120 would be 57,600. Okay. And so yeah, this is scalable up from 12 to 30. And that's what we calculated. So it looks like those of you who work on designing populating panels and panel schedules for buildings, your panel schedule might look like this for distributing your load amongst the current amongst the various phases. So let's now. So with single phase, it's pretty straightforward on a three-phase panel, as long as you're 120 volts. Now chargers are all single phase for the 100 for the AC charger, level 1 and level 2. They may be at 208, they may be at 240, which mean on a 120 208, they're going to be single phase line to line. So that's a little bit different. So let's take a look at that, connecting line to line. But first, let's go one more time at the 120 volt charger. If we draw our Y connected source here, 120 208, and we got neutral 3 lines, and let's connect the charger, and we identify our line currents, and we identify our neutral current as being the sum of the 3 line currents. So now we connect in a neutral, and we connect in a charger here between line 1 and neutral, and we get a current in line 1. So that means the current in the neutral is going to be equal to the current in line 1. Okay, I line 1, that's the neutral current. What we're looking at is the effect of adding chargers on the neutral current here. Okay. Add another charger. And then we got IL2. So now I neutral is IL1 plus IL2. Let's add in IL2. That's 120 degrees out of phase. So the neutral current is the sum of those two, and that's vector sum or phasor sum, however you want to say. And you can see that that's an equilateral triangle. So the neutral current is still equal to the magnitude of either one of the two individual line currents. And so now we add yet another, there's your neutral current right there, as you can see, the sum of those two. Then we put another charger in. So now we got three currents contributing to the neutral current, and the picture is going like this. IL1 plus IL2 plus IL3, neutral current is 0. Okay, so nice balanced load, everybody's happy. There's people who are talking about upsizing the neutral when you've got because of harmonics in the current that goes to the chargers. Well, maybe so with level 1, but for the most part, what we're looking at is a balanced load. Your neutral current is going to be 0. But at worst case, well, that's another story. But in the ideal case, we got 0 neutral current when we have purely resistive loads here. Okay, so what about we have 40 amp 208 volt chargers? This probably looks familiar. This is pretty common for doing a panel schedule like this to see what kind of current is on the lines. And concluding there's 160 amps on each line. On the other hand, let's do the math here and see what we get. We know that for a balanced three-phase system, the actual volt amps is 1.732 times the line current times line-to-line voltage, or 57,641, not 49,920. So wait a minute now. That's 160 amps giving us only 49,920 instead of 57,641. What's going on here? This doesn't seem quite right, does it? So this says we got to be a little careful if you're going to do a three-phase service with 208 volt chargers on it, because, all right, why are the two values different? Let's look. Let's say we got these chargers, and how many can be connected? And let's do it one at a time, okay? Here's one here now. Got 40 amps. Okay, now let's connect another one. Now, we know we just did it. We added IC1 and IC2. But this time, it's not going back on the neutral. But the current going back to VA from IC and IB is not 80 amps, but it's 69.3 because the current coming out on IC and IB is out of phase. Okay, by 120 degrees. And when you do that, you get this 1.732 factor. And that's, I know, I'm sorry, I'm getting you back to your beginning circuits course, and nobody wants to do that, but that's why we teach that thing in electrical engineering, is that so everybody knows what the square root of 3 is equal to. But if you put a clamp-on ammeter here, this is what you would see on the unused on I sub A. IC, there's only one load connected, 40 amps there, 40 amps there, but 40 plus 40 equals 69.3. And that's what your clamp-on ammeter is going to tell you. And now we add another one here. And now all three lines are at 69.3 amps. All right, because each line is supplying two chargers. that is one end of two chargers. So 3 lines, 3 chargers with 2 ends each. 3, 10, 2 is 6, right? Wow, pretty tough math here. Okay, so here's the key. Instead of 80 amps, we're looking at 69.3. And that's where that problem came in with the both amperes. So now, if we put in more chargers, in other words, 80 amps on each one, that's 2 chargers across each line, we're at 138.6 amps. Okay, with a balanced load. And that's within the 160 amp limit. So we know that we can do 6 chargers. Okay, but what can we do 9? That's the question. We're good. Do the math check. 49,920 volt amps. And they both add up correctly. But can we do 9 chargers? And the answer is, well, current is 138.6 amps, not 160 like we thought it might be. But can we add 9? No, we can't do 9. But let's look at a little bit more math here now. What we know is for balanced loads, and if we stay with balanced loads, we can determine the line current is simply the total power divided by 1.732 times the line-to-line voltage. Okay. Again, this sort of thing you may or may not digest it during this session, but if you're serious about it, you take it home and you take your computer or your laptop to dinner tonight and you show it to everybody and say, hey, look, you guys are going to really want to know about this. And that way you get everybody's captivated attention. Nobody's going to say a word. They're just going to be totally amazed. And you'll be the star of the show. I may believe that that's probably true. Here's a chat. Let's see what we got here. What's the diversification factor? Sorry. What's the diversification factor? Oh, like if say I live in a condominium, we've got 43 units here, and each unit has to have a certain power for their water heater. And normally it would be 4,500 watts, but at 208 volts or less than that. But let's just say 4,500 watts. Point being that when you have 43 units, everybody's not going to have their water heater running at the same time, and everybody's not going to have their air conditioning running at the same time, and everybody's not going to have everything else on at the same time. So you're allowed to run less power into the building than one would get by simply multiplying the needs of one unit by 43. In fact of the matter is, it's down in the 35% range. So that's why this 40%, okay? The 40% says that even though you've got all these loads in your house, the likelihood of you having them all on, we're going to say, all right, we're going to allow you 100% for 8,000 watts. But all those remaining watts, the likelihood that all those are going to be on at the same time is less than 40%. And I've done the measurements. I've actually changed out a main circuit breaker in the house and turned everything on to see how much power would actually show up. It's nowhere near the rating of the circuit breaker. On the other hand, I've seen in certain businesses and like in a restaurant, sometimes those circuit breakers come pretty close to being fully loaded. But in residential, the diversification, it's simply a matter of recognizing that everything doesn't run at the same time, so we don't have to add them up in a linear fashion. We can multiply by a diversification factor. And hopefully that answered that question. And sorry, that's probably been up there for a while too. I was expecting my screen to flash for a question and it didn't. So I'm glad I looked. And thank you for asking. Oh, yeah, okay. Escape on my keyboard. I'm afraid to do that. I love full screen. but others might want to do that. Good point. Okay. All right, let's see where, okay, that does that. All right, so here we go. Loads are unbalanced, and then you use, if let's say you have 5 loads you want, you should, if you calculate for 6, then you're okay for 5 or 4. But if you have 3, that's fine. But if you move to 4, it's a good idea to calculate on the basis of 6 and assume things are balanced. That way you can't go wrong. Because at least one of your line currents is going to be what it would be if you had 6. If you have 4, at least one line current is going to go up to the value it would be with 6. Okay. So one load, then you can use one load to estimate the highest line current. From 2 or 3, then you just use 3 loads to estimate it. And 4, 5, or 6, you use 6, and so on. Okay. And if you don't have a unity power factor, then you have to multiply by power factor. That's another story. I've not seen any of these that indicate they have a power factor. Okay. Now, if it's VA, volt amperes, that's just 1.732 times IL times VLL, because volt amperes already takes into account the power factor. All right. So if you know the volt amperes the thing is drawing, then you still can use 1.732 times IL VLL, and you're assuming that the volt amperes represents the power, but in fact, it could be more than the power. Okay. So maximum allowed charger currents keeps the loads balanced. So the load's up to 160. And what that says is if we went to 160, if we try to do 9 chargers at 32 amps each, we need 166.3 amps. Doesn't quite work. That would be fine with a 225 amp service, but doesn't quite cut it with a 200 amp service. But if we could reduce the load on each charger by 1.21 amps, you could add 3 more. So subtract 1.21 amps from each of those 32 amps. That's not much, is it? I mean, that gets you down to 30.8 amps. And by the way, remember that number 30.8, just in case you happen to take a quiz. That just might show up on a quiz. You never know. Okay, so this would be neat then if you had a little dial on that charger that said, hey, I want to use 9 of them. Or if you had the chargers talking to them each other, it says, hey guys, amongst ourselves, we must limit our total current coming into this panel to 160 amps. And by the way, the panel has 3 current transformers on its feeders that will tell us exactly how much current is coming in, so we can flip a coin amongst ourselves and decide how much we're going to use. And that's all part of the fun of the communication protocol amongst these chargers. All right, and the neat thing about this is amazing. Well, we're going to do a condo calculation here, and you're going to see how simple this gets. So, bottom line is, a little demand management could be really helpful. And that's exactly what's out there. Let's look at a condo parking area. This is my building. So we've got a 800 amp 12208 3-phase common area service. And this is a part that's not backed up by the backup generator. All right. So all we need to do is determine whether there's any room for any additional loads. So how are we going to do that? Well, we have a general service demand utility rate. So we look at our utility bills and collect the last 12 months of them, and we determine the highest demand over the last 12-month period. Then we apply NEC 220.87. This is really complicated, isn't it? We're going to have to look at 12 electric bills and find out which demand is the highest of the 12. I mean, that could take it up to a whole minute to look through and get that information. It might take a little while to get the utility bills, but once you got them, then you add the chargers until the limit is reached. So, and then make sure that everything is consistent with the bus bars and the feeders. All right, so let's do it. Let's just do it. Okay. And each individual unit's the 12208 single phase coming off this three-phase system. But we're looking at the separate transformer that's feeding the building, the 800 amps, three-phase, 12208 for the building, and here's your bill. What do we got? There's the demand. Kilowatt hours used, demand KW. How about that? Look at that, 84. Wow. 84. 84 kW. Well, what does that mean? Well, we can figure that out. We first of all, we have to multiply that by 1.25. All right. And that's 105 kW demand. That's the amount of demand on this 800 amp service. My goodness, how many amps is this anyway? 105 kW? Let's do a little more math here. Let's see, the current is power 105,000 watts divided by 1.732 times. That's 291 amps. We have got 800 amps available, for heaven's sakes. And we're only using 291 on the worst case, worst month of the year. Wow. That leaves a whole lot left over. That's 500 amps left over, except for the fact that we can only use 80% of that. Ah, what a shame. That means we've only got 407 amps left. Well, all right, so we got 407 amps left. Let's see what we can do with it. We could do level 1 chargers, maybe. Now, those retired people don't drive more than 30 miles a day. How many of those could we use? What time is it? 3:14. 45 minutes. Okay. How many of them then we know that's the easy part. We know how to do that. Keep the load balanced. 120 volt Y connected line currents, same like we had before. 407 amps. That means 25.45 chargers on each phase. So we get 25 chargers per phase, or 75 chargers without any fancy load controllers or anything. This 75 chargers, we can run continuously all day long. We got 43 units. And in our case, to charge our car overnight at 5 miles an hour takes 6 hours. So in effect, we can charge about 3 times as many cars. These 75 chargers, we could charge 75 cars all day long. But if you took those 75 cars after they're charged up after 6 hours and pulled in 75 more, and then 75 more, we got 225 cars we can charge up with this. So that's not too bad. It's a lot of shuffling of cars around. Probably not going to do that, but it's one option. All right. So and of course, this is 25 per phase, is 0.45. You know, we could actually get if we could back off to 15.65 amps instead of 16 amps, then we could put 26 chargers per phase if we had a way of backing off. So the point is, there's a lot of electricity available here, isn't there? How about level 2s? Let's take a look here. Let's put in 40 amp units in multiples of 3. So we know that every 3 of these is 69.3 amps. So if we take our 407 and divide it by 69.3, we get 5.873, which we can't round up to 6. We have to round down to 5. So what this means is we can do 15 chargers. And that's going to use up 346.5 out of 407 amps, which leaves like, what, 50, almost 60 amps for level 1 charging or something else. But in any case, we can do 15 chargers. And these are chargers that will charge a car like mine in 1 hour with enough electricity to go for a day. Actually, it'll do mine in about half hour. So, because we don't drive very much, we're getting old and we just try to stay around home. But the average charger, we can do 15. Or alternative, we're going to have 15 charger circuits available. And each circuit can have, say, 4 chargers on it, each of which will talk to each other such that they limit the current so that only one charger is working at a time. So we can easily handle 60 cars, 60 cars, charging at level 2 in a day's time on this single 200 volt, 200 amp, 120, 208 volt, 3-phase panel. And work out a deal with the building for paying for the charging. This is what's possible. Most people won't believe this, but you've got the numbers right in front of you and you go over them again and again and again. And all you need to do, if you're in a condo, or if you go to a condo, and if you can convince them to look at your electric bills. I looked at the electric bills for the condo next to us. They're running less than 50% of their side of their service as well. So what are we going to do with the 60 amps extra? Well, we put smaller chargers in if we want. Let's charge all the motors, all the scooters and the bicycles and everything else. Or level 1s. In any case, look at what you can do. 30 times 365, 10,950 miles a year for 1 hour of charging. Or 10 hours at night in a year, that's 109,500 miles of charging if you drive your car a lot. And 10 hours at night on level 2 at 40 amps. And 15 chargers operating 10 hours a day, that's 4,500 miles a day. And if it operates 24 hours a day, they can get 10,800 miles a day worth of driving out of those 15 chargers. Boy, nobody would be home at all. I have a building all to myself if people are out driving that much every day. So interesting numbers, and I invite you to digest them because they're really important. Okay? So clearly, we want the chargers to talk to each other because none of them are going to need all that power for all that time. Okay? And of course, if you want to mix level 1 and level 2, you can do that too. So here's just an example here. If you want to take a look at how many level 1s can we add in with the level 2s. All right. Now, here's another interesting thing. People might say, well, you have to connect to your own unit. And that becomes a problem. Okay. And the reason why, and I want to share, here's where diversification becomes an issue. Because this is what you'd want to do. You'd want to maybe do a line side tap on the feeder at your meter. I mean, our electric meters are right next to our garage, so it's easy to do a line side tap at the feeder, at the main circuit breaker, and put a a 40 amp disconnect or something within 10 feet, the way this line side tap rules work. And then you calculate the dwelling unit the way we just did it, but that adds 40 amps to the dwelling unit load. And when you add that 40 amps to the dwelling unit load, there's only one interesting thing here. If you use 220.84 demand factors, you find that the demand factor for 8 to 10 units is 43% and 28 to 30 units is 33%. So what you end up with is like a 1200 amp service for 30 units. All right. And if you got a 1200 amp service for 30 units, and then you start adding 40 amps to each of 30 units, there goes your 1200 amps down the drain. So it becomes an issue, and in my opinion, it is not a very smart idea in a condo to start adding these units, chargers, to individual units unless they have some really good communication amongst them, such that they are talking to the current that's coming into the meter system, say the 1200 amp meter bank that feeds half of the units, say 20 units on a 1200 amp service. You're going to have current transformers on all three legs of that 1200 amp service and make sure that current does not exceed 80% of the rating of the feeders. And that gets to be fun because when you got 1200 amp feeders, that is not going to be a single piece of wire. You're going to probably have at least 3 to 4 pretty fat wires in a parallel connection on a feeder. So that's a lot of current transformers or one big ones and whatever. So it gets complicated and probably not worth it, especially when you have all that leftover in the house load, if you have it that. So anyway, that's my suggestion if you're going to try this is check that out later first because it's easy. If you're on a general service demand, it's easy to do calculation to see how much leftovers you've got and then see how you can do with it. And then work out a deal with the condo association for the owners to pay the condo association for that electricity. And there is a deal such that most, sometimes you can't have third-party sale of electricity. But in most areas now, you can do that. Your condo association could sell you electricity for, say, 10 cents a kilowatt hour and make a few bucks on the fact to pay for installing the chargers. Or even 15 cents a kilowatt hour, which is what you'd pay anyway if you plugged it into your own residential rate. And so then your condo's making 7 cents a kilowatt hour for every kilowatt hour to help pay for the installation. So then they don't have to fuss about these EV drivers, even though the EV drivers are dumping a whole lot less carbon dioxide into the atmosphere, and don't get me going on that. Okay. Anyway, nice to have the original electrical designs drawings, Andy. They give you a lot of good information on what's in there for your riser diagram. So back to the condo example. Here's what I've just done. I'm not going to go into detail on this because I've just explained what these are saying. And if you want more detail on this, just read it through a little more careful. But you can see what's left over here. Uh, uh, one of our two 1200 amp units is connected to 21 units and the other one's connected to 22 units. So the 21 unit has a 37% demand factor, the 22 unit has a 36% demand factor. And the calculated load for the original 21 units is 1057 out of 1200. That doesn't leave much left, does it? And the 22 unit center is 1114 out of 1200. Okay, which works fine on this diversification thing because we're not talking about continuous loads here. But this is based on 24/7 occupancy of the units, which, well, okay, that never happens in my building, but it comes close during the holidays, New Year's, so forth. But a lot of folks from up north go back home. We're not normally 24/7 occupied. You could probably factor that in one way or another, but that would get pretty complicated. You'd probably need a year's worth of data anyway to make sure you didn't mess up. In any case, 114 amps left for the 21 unit center and 68 for the 22 unit center. And that's before you take the 80%. So maybe you could put in a few level 1 chargers, but not a very good idea to go much beyond that. Now, here's the interesting thing now. What about a restaurant? Well, that's kind of neat because you park there for 2 hours and or park there for an hour and a half to dine, and you get on a level 2 charger 30 miles of charge. which is worth 30 miles of charge, is like at maybe, let's see, what are we saying? 4 miles per kilowatt hour, 3.5 miles per kilowatt hour. Let's just even say that's 10 kilowatt hours. So that means the restaurant, in order to charge your car, 80 cents. Add that to your tip, whatever. But you got enough electricity to get home. And then you move and somebody else parks in that spot, plugs in their car, off they go. Or maybe that's such an attractive feature that it brings so many EV owners to the restaurant that they can barely seat everybody. And maybe it's worth it to them to even give you free electricity with your meal by simply upping the price of the meal by 1%, or who knows what. A lot of interesting possibilities here, aren't there? All right. I mean, this is like that parking garage that at the medical office where one time I actually found an open parking, an open charger, and I plugged in, and then I got free electricity for my car. I won't tell you what the doctor's bill was, but then again, I only needed about 10 miles of charging, so my free electricity was worth about 15 cents, maybe 20 cents, something like that, but or 30 cents, who knows. And anyway, it's a nice feature, and I think when there's more and more EVs around, this is going to be an attractive thing for restaurants and other commercial things to have. And now you all know how to figure out how to wire up for a restaurant either. Also, they may have 10 chargers going at a time, or you may have one 5 parking spots with EV chargers, or 6 parking spots with EV chargers, and all with open charge point protocol. So they talk to each other, limit the charging, and they share. And in a matter of an hour's time, each one at least gets 10 miles of driving, which is, yeah, most people don't drive much more than 10 miles to get to a restaurant. So it gets you home again. So anyway, it's interesting for restaurants and stuff. On the other hand, we go to a motel, that's another story, because there these folks are going to want to fill their car with somewhere between 200 and 400 miles, maybe, so they can get out and drive the next day, if they're just passing through. So that's another story, and you need to take that into account when you do the design. But with the tools you've got at this point, you can probably do that. Okay. So 7 hours at level 2. That means that level 2 charger is not going to be shared by anybody else very much. Maybe half charge, maybe half of it will be shared with somebody else. But you're going to have a little more available power in a motel than you are in a restaurant. Level 3, fine. We'll leave that up to the guys out on the turnpikes and the freeways and stuff, because that's expensive stuff, and there's the numbers go along with it, and they're pretty specialized. And the intent here was not to spend a whole lot of time on level 3, but get people familiar with at least a straightforward method of evaluating whether it makes sense to go with level 2 instead of level 1, for example, and whether or not you have to have a separate circuit for every car in the garage of a condominium. No way. You don't have to do that. We now know that. You can probably put, well, Tesla, generally their chargers like to 4 of them like to talk to each other, but there are other charger manufacturers where you can put 18 chargers that communicate with each other. So you got to do a little shopping around and see who has what available. Okay. So what else should we be thinking about here? What if the service size is inadequate? Well, you just might have to increase it. Might have to install a new one, might have to have a new transformer even. Talk to utility about that. And if you're bumping close to your total demand, doesn't hurt to check with the utility, make sure they haven't diversified the transformer size. for feeding your 800 amp service. Maybe their transformer won't do 800 amps anyway, because they know very well you're not going to use it. So that's worth checking, and utilities are generally pretty cooperative in giving you that information. And who knows, there might be some delays due to demand for new services. And then there's also the interactive systems, and yeah, they sure do that. Good idea. Um, and what if you got a photovoltaic system with ESS? What's that acronym? Hmm. Oh. Well, that means that the PV system can talk to these things. And so that makes it especially neat. Tesla and Enphase, for example, are two of them that I'm aware of that have this. And that they all have these communication links. Okay. So that the charger charges when the PV is cranking out like crazy. And let's say utility only wants to pay you at avoided costs or something for electricity if you sell it back. Well, then if you can dump it into your car at that point, then you don't sell it back for that cheap price. You charge your car with it. And then later on, a couple of years from now, when utility wants that electricity at peak time, then their substation contacts your vehicle and negotiates 20 cents a kilowatt hour to buy that stuff for peaking electricity, which is still cheaper than what they'd have to pay for one of their other peaking sources. So anyway, you got to read the instruction manual. That's what it's all about. If you don't read that, you can get in real trouble, and read the specs. And it helps to understand some of the stuff previously discussed, because now hopefully everybody can pick up an instruction manual and an installation manual and equipment specifications and make sense out of them. And that really does help, as you all know, to be able to make sense out of all this documentation. So, and of course, not everybody charges every mile that they drive at home. So give a little thought to how much do you charge your car away from home in terms of what you need to provide at home. So what are some of these options here? We've been talking about commutation control, stuff like that. Let's check the time. 3:34. Oh my goodness, we're doing really well. We're moving right on. We may have some spare time. And I'm gonna check and see if we have any. Nope, no chats. So we can hold off here. So it looks like we may have a little extra time to discuss things. So if you have any questions you want to talk about, write them down so you don't forget, or get them in the chat. And we'll use whatever time we have available, if you want it, at the end, to go over some of these things I went over a little faster. And by the way, I do have at the end of this an appendix. If you really love three-phase power and you really love phasor analysis, and if you really love electrical engineering, if you're an electrical engineer, you can read through that stuff, because it's the documentation for those numbers I just kind of threw out at you, the 1.732 stuff. But there's a complete phasor analysis at the end of this that you can go through if you're just got your degree in electrical engineering, if you got a little while ago and loved that stuff when you took your power course or whatever. So all this stuff is really useful to have. And so it's the kind of thing that you really want to have, if at all possible, in your charging equipment. And for the most part, it's there and it's coming. And you know, I'll tell you what's here now, but it's going to change tomorrow, because this is a rapidly changing field. But power management is incredibly important, and we're getting into that a lot in PV now. That's what I do for my other half of my retired life, is I review plans for photovoltaics installations, and we're doing a lot of power control systems now, where we've got current transformers on the production and on the consumption, and we measure that and make sure that we don't overload anything or that we have power available when needed. A lot of stuff when you got that instrumentation, you can do some really neat stuff. The bidirectional charging is here. I say it's on the horizon. It's here now. California just approved it, encouraged it. But the point is, all the rules are there. The rules are there in IEEE 1547-2000. The rules are there in the National Electrical Code. I showed you in Article 625 where it is. So the rules are very clear, and it's very simple that if you're going to sell something back to the utility, the inverter that is converting the battery DC from your car into AC for the utility has to meet IEEE 1547 requirements. And basically that says it has to be a current source instead of a voltage source. It has to synchronize with the utility voltage, and it can't overload the feeders in the opposite direction because in effect, the feeders, instead of carrying electricity to you, they carry electricity from you and they become transmission lines instead of feeders. And that's an interesting concept. So, okay, and lots of different ways to pay for these things. And as we point out, some people are using them as an incentive to come use their business because it gives you some free electricity. You buy yourself $100 meal and they'll give you $1 worth of electricity to charge your car. How do you beat a deal like that? Of course, it costs them a little bit to invest in the chargers, but then again, they invested a little bit in their tables and their dishes and their kitchens and their everything else. Maybe that charger is a small part of their total operation. So, and I'm sure if they do the math, they'd find those chargers pay for themselves relatively quickly in terms of the increased business. So, let's look at two load control methods currently. Each one monitors a feeder current to the distribution panel. One is the uniform distribution method that says if you got 12 systems out there that I see there's a question up there. I'm going to come to that in a minute. Let's say you got 12 cars plugged in, but you got limited current. It divides that limited current by 12, and each one gets 1/12 of it. What do we got? What do chargers cost? Well, Lori, the charger I got with my car came, the level 1 charger was free. I mean, not free, but it came with the car. And the outlet to plug it into is no charge. Otherwise, chargers, depending on level 2's, typical charge, I think is, and maybe some of the other EV owners can chime in on this if you would, if you recently had a level 2 charger installed, maybe you might comment on what you paid for it. What I've seen advertised prices are somewhere in the $500 range, but if anyone has any of the 4 EV owners, if you're in single family detached and you have a level 2 charger, what did you pay to get that installed? Or what did you pay for the charger if you plugged it into your dryer outlet, for example? And if you'll just type that up into the chat, we'll get maybe a better answer to Lori. But the charger itself, if you Google level 2 vehicle chargers, depending on how many watts that level 2, whether you're talking, or how many amps, or you're talking to 30, when I say 40 amp, I'm talking about a 32 amp charger that uses a 40 amp. You get some on Amazon for $500 installed, 15 to 2,000. Yeah, okay, that sounds about right, Nick. Yeah, that's what I've seen. $500. And if you've got an existing dryer outlet in your garage, for example, you might be able to just plug that thing into your dryer outlet and then plug in your dryer when you need the dryer. You're not going to use your dryer at night anyway. And only if you're over 60 amps do you have to have it fixed. Otherwise, you can plug it in. So, and some fancier ones are more than 5, but even the 500 gives you lots of communication, a lot of interesting capability. So if you amortize that $500, that's you're going to save a whole lot more than that in gas your first year of driving, probably anyway. So that kind of puts it all into perspective, and is a really good question. I'm glad you asked. And others who might chime in, feel free to type it on in. So the uniform distribution method is simply the chargers talk to each other and say, okay, say there's 12 of them and one car pulls up and they plug in and nobody else wants any. So that full charger gets full charge. First charger gets full charge. You charge on that car and then another car pulls up. So then they split the amount 50-50 if necessary. And then at some point, car number one pulls away and car number two gets more. And you see the drill here that everybody gets the same amount. You divide the amount available by the number plugged in. The next would be that you simply have to maintain it at less than the preset maximum. And it's great if you're charging a fleet of cars overnight because they don't care who's getting charged when, just so they're all charged by morning. All right. Then there's the first in, first served method. It says maximum charging until system max is reached. Like say you can charge 6 cars at a time, but you got 36 outlets. Those 6 cars, they charge up, hour each. They're done. The first one is done. So number 7 comes in, takes over. And I think you can see the picture on how the first come, first serve works. Either one, the uniform distribution, generally better for fleet. First in, first serve is where you've got sort of random arrival at the chargers. And my guess is the first in, first serve method is probably what they have in that parking garage that I parked at. Because as soon as the vehicle is full, the next one in line gets charging power. So, like it says, overnight charging, the first in, first serve works just fine. Because people are going to come in at kind of random times rather than everybody showing up at 5:30 after they get back from work and plug in their mail delivery truck, whatever, or their bus or whatever. All right, and not having to move the vehicle is very convenient. If one charger can do 12 vehicles without having to have somebody to pull one up for an hour and then move the next one in for an hour and then move the next one in for an hour. Interesting job, but yeah, a lot easier to have an electrician put in 12 chargers that talk to each other instead. So, Blink is one of the charger players. I don't work for Blink. I don't sell Blink, but they just happen to have some nice pictures on their website. And they had some specs, and it's interesting to look at, here's what they've got. Internal meter to monitor energy demand usage. Nice to monitor demand usage. You can say, okay, I'm going to limit my demand. And maybe I want this thing to put out full charge, except at 5 o'clock, I want it to back off because then I'm going to have to pay more for my demand charge. All right. So, and you can do lots of nice analysis and stuff. So, neat piece of equipment, a lot of interesting stuff in here. And it's like I say, if you're considering one, this is what you're going to read about. And you can see smart grid implementation and support for commercial use. Wow, ability to manage multiple charges with detailed data sets. Wow, so there's a whole lot behind, lots of safety and compliance stuff, promotion, advertising, cold load pickup. That's kind of interesting too, because like up north, cold batteries have a little bit higher internal resistance. So when you start charging them, you don't charge them quite as fast until they warm up a little bit. And when they get warmed up a little bit, then their internal resistance goes down and you can charge a little faster. So that's an interesting thing as well. I'm guessing some of you maybe live up where it gets cold once in a while. Last time I looked, it was 85 out here, I guess, here in South Florida. But anyway, here, just so you get an idea of what you'll find when you look at these things. A few more specs. Nothing like having a nice little remote thing to tell you exactly what's going on and where the nearest charging stations are and stuff like that. So energy management, network product, customer support, safety, a lot of good stuff in these things. And you know, this is typical of the chargers out there. I don't need to show everybody. Compare Blink with everybody else and then decide who you like. Okay? So there's a lot of EV charger, Tesla, you know, who heard of those? Few of those are out. But Tesla's not the only ones out there. So anyway, here's the basic one-way charger. Plug it in, charges your car, converts AC to DC, and charges up the batteries. And batteries drive a nice DC motor, Series 1 DC motor. That's why these electric cars have incredible starting torque, because they have DC motors, Series 1 DC motors. And electrical engineers who remember their motors class, you remember that when you put the same current in both the rotor and the stator, you get the square of the torque. And that is huge. And that's why you get this amazing acceleration at a stop sign. And it's fun to well, kind of fun, but kind of almost you got to be careful, because some of these cars are really got a lot of pep to them. Anyway, here's a bidirectional, just so you get an idea. You got some external bidirectional charging circuitry now that will actually accept power coming back to it as well. So you see the directions, the communications go both ways. Basically, you pull in, plug in your car at 9 in the morning. By 10 o'clock in the morning, it's all charged up, or maybe it charges slower and it waits for a nice peak of solar power to come in at noon. And it charges up by 1 o'clock. It's fully charged, waiting there. And it's still parked in at 4 o'clock when utility knows that it's parked in, because it has this communication line to the utility. And the utility says, hey, we're running a little short now. We could use a little extra kilowatts here. What do you have to offer? Could you maybe sell us 5 kilowatts? We'll pay you a demand rate on this. And well, we'll offer you, say, 15 cents. And your car says, 15 cents? Are you kidding? Last time I got made 25 cents. And the utility comes back, well, okay, how about 20 cents? And finally, they settle at 22 cents for that kilowatt for an hour. And so, or maybe 5 kilowatts for an hour. So you're going to deliver 5 kilowatt hours. And you put at the demand charge of 20 or at 20 cents a kilowatt hour, but maybe a demand charge on top of that. And for 5 kilowatts, and maybe you're paying a demand of, well, you know, it's the demand per kilowatts can be kind of expensive. But anyway, and all this is taking place in a few milliseconds in communication between the car and the utility, with only a little agreement that you've got between the utility and the car, that the car is going to make some wise decisions. And everybody wins. Utility wins because they don't have to worry about having spinning reserves that is not connected, but still burning fuel. The car owner wins, the planet wins, everybody wins. How can you beat a deal like that? So anyway, usually I say that's the end of the story, but I'm sorry, guys. This is the beginning of the story. So what do we got here? It's 3:50. We got 10 minutes. If anybody has anything you want to talk about, let's here's a couple of chats. Let's see what we got. Get some Amazon 500 installed. How does first cost of EV compare with comparable hybrid or gas car? First cost. Let's see now. I would say that it's fairly comparable. Our car, the sticker price on it was 40,000 for the nice model, And we got a $7,000 tax rebate, so that brought it down to about 33. And if we had bought a similar gasoline car or hybrid, probably would have cost about the same. The cost of electrics is coming down. It would come out down a whole lot more, but there will probably be tariffs on those that might come in from China, Japan, other places. But the first cost is not bad. And then, of course, there's the thing about, well, what about the additional energy costs? What about the tires wearing out faster because the tires are heavy and all that pollution from the tires? Well, one thing is that the rubber from the tires is not a greenhouse gas. So that's an advantage. And yes, you may have to buy more tires. And the estimates I've seen in terms of energy payback time on these things for the additional energy that might go into them for their construction over gasoline is 2 to 3 years. So beyond that, you're home free in terms of carbon dioxide stuff. So let's see, Phil, what do we got here? Recently worked on a project that had a fuel center with gas pumps and proposed bank of EV chargers. Local municipality had a rule in place where a certain quantity of EV chargers exceeded their definition of electric substation. So the project owner scrapped the EV chargers from projects. Ooh, that's interesting. This is the first I've heard of that. I love it. That is really interesting. Um, it should, the local municipality, okay, maybe the local municipality this is, normally municipality has nothing to do with the power unless it's a municipal power system. We've got Lake Worth Power up the road from me here, and Orlando Utilities Commission and Jacksonville Energy. So if it's a municipal, one thing we find with municipals is that the folks who do the negotiation generally are not very highly technically skilled. And a lot of education needs to be done. I can see how it could exceed a definition of an electrical substation if in fact the EV chargers are going to send electricity back to the grid. But that's a control issue. That's a power control issue. And that should be something that's negotiable and should be able to be worked out. So let's see, could it be related to the feeders? And yeah, it can be related to the feeders. And that's why, I like this. Yeah, we're in this world of competition, whereas it's time that we start cooperating. And I put together a program a week or so ago in terms of for energy storage. And the idea is that if you look at if you believe in global climate change, and I happen to believe in it because I happen to understand exactly how it works, and we're dangerously close to a runaway level here, and we're in a case where if you have, say, 5 players in a game, and if we're all on the same team, then we all 5 win. Whereas if we don't do this right, then we all 5 lose. And what we don't want to have is a lose deal. And so my only comment is that these folks need to be sitting down with their technical people, need to be sitting down with some technical people, understand what they're doing, whether it's from the EV charger manufacturers, whatever. They need to say, what is your problem? How can we help you solve it? And then you sit down and you solve it, because that's what engineers do. Does everybody agree with that? We solve problems. Let's see, do we have hand raising here? I'm going to open my participant box here and see if any. Yeah, we have hand raising. Does anybody who doesn't agree that engineers are supposed to solve problems? Yeah, Jonathan, I agree. Thank you for agreeing with me. One person, Nick agrees with me too. Thank you. How about you, Ashley, George? David, yeah, all right. So let's team up here, guys. Let's solve this problem. There's so much misinformation out there, and people worrying that we're going to lose money on the deal. Believe me, if they don't get on the board and cooperate and we all work together, everybody's going to lose money. Whereas otherwise, everybody's going to breathe clean air and make money and go where we need to go. And our grandchildren and children are going to live a whole lot better life if we do this right. So, all right, let's see what else we got. Oh, our participant box is closing, covering. What are comparable maintenance costs for EVs? Well, first of all, how long do car batteries last? What's the replacement cost? Well, I can't tell you exactly. Generally, it's judged in terms of the number of cycles they will do, and lithium batteries are typically good for 10,000 cycles. That's full charge, full discharge. So what that means is it's not necessarily a number of years, but it's more of a number of cycles. And if you get 50 miles to the charge, that means 10,000 times 50. Well, gee, that would be about 500,000 miles, wouldn't it? And I think this almost bears out because I've heard of some experiments they've done with some fleets of Teslas in California where they're getting 400,000 miles. We're nowhere near that with our car. We're 6 years into it, and we see some degradation of the batteries, maybe, but we don't even know that's true. But it's just the way the gauges on the car measure it. So let's see, comparable maintenance costs for EVs. Well, never have to have your radiator fixed, the carburetors, distributors, tune-ups, all that kind of stuff. Electric motors are just don't need much. In fact, dealers are going crazy trying to figure out what do you do to maintain an EV. So that's another issue that needs to be dealt with is how does a dealer transition to EVs when they require significantly less maintenance than a gasoline powered vehicle. And I have no idea. We paid an annual maintenance fee for our car, but we have no clue what they did for the money they charged. And it seems, but then again, we're a plug-in hybrid, so whatever they did may have played around with some of the gasoline stuff. But maintenance on EV, they say the tires wear out a little faster because of the heavier car. Other than that, the rest of the components generally last a little longer. Safety, some data out there saying that EVs are something in the neighborhood of 4 to 5 times safer than gasoline vehicles in terms of fires, all that kind of stuff. What is carbon effect from gasoline car? Thank you. Gasoline. Well-known fact, gallon of gasoline dumps 19.6 pounds of carbon dioxide into the air. Every gallon of gas, round numbers, 20 pounds per gallon. All right, so if you get 20 miles per gallon, that's 1 pound per mile. Electricity generation for EVs. The typical electricity generated for electric vehicles nationwide, most electricities or most utilities are moving off coal to natural gas, and there's a lot of nuclear and solar coming in now. So the average per kilowatt hour, pounds per kilowatt hour of carbon dioxide for EVs is 0.92, as we showed in an earlier slide. And so that's 0.92 pounds for about 4 miles, and instead of 1 pound for 1 mile. So we're looking at 75% reduction if we're using electricity bought from a utility. And of course, if you're charging with solar electricity or renewable electricity, then there is zero carbon effect. It's about a 2-year payback to pay back the cost of creating that solar electricity with the equipment. And then from there, it's home free. So there's your carbon effect question. And anybody else? It's 4:01. We start at 4:02. So it looks like we can call this off. There will be a quiz. Be sure to look at the rules, how to get the video available. Oh, yeah, here we go. Okay, here's the host. Don't use Edge or Internet Explorer browsers. And if you have questions, comments, there's you can get the video available and in 24 hours. And so, and the slides, of course, are in the video. And I think there's also an evaluation questionnaire on the website. Appreciate if you fill that out too. I'm a former college professor, and I used to always pay careful attention to my class evaluation and try to uh, do whatever I can to make people happy. Okay, so folks, thank you very much for joining us today, and I guess we can call it a day. This will be it. So thank you, everyone. We are now officially finished. I'm going to leave myself connected until I see the number of participants drop to 0, until just in case anybody has a last minute question. Phil, thank you. I'm glad you felt it was worthwhile. Okay, webinar's over.